related to each other. Okay, so this is of autocorrelation. So non-autocorrelation is a stringent assumption. When we will go for real life data analysis, under many circumstances, we will face the problem of autocorrelation. So our objective is to understand what is the meaning of autocorrelation, what are the consequences of autocorrelation. Now, given the database, how we will detect autocorrelation, and finally, what will be the remedial technique? If we detect there is autocorrelation, what will be the remedial technique by which we will be able to find out a best linear unbiased estimator? So among these, last day, we covered two things: what is meant by autocorrelation, and number two, what are the consequences of autocorrelation? What are the consequences on the OLS estimator? So we found that beta hat OLS is still unbiased. However, the minimum variance property is not retained. Number three, there will be serious problem in estimating T statistic if we use the OLS estimator beta hat before taking any remedial measure. Okay. So last day we completed these consequences, and today first we will learn about how to detect autocorrelation. Once we can complete this thing, we will move for what will be the remedial measure in context of autocorrelation. So let's first start with the detection mechanism. There are several mechanisms, several tests by which we can detect autocorrelation. However, here in this course, I'll introduce a widely used technique called Durbin-Watson technique. Now, DW technique has also some limitations. So it appears under several circumstances, we will be not able to use DW statistic. Maybe we need to use a modified version of that or several other measures. Okay. However, in this course, you will have a single test, Durbin-Watson test, DW test. How to detect autocorrelation using the Durbin-Watson test statistic. Because for the rest of the estimators, you need, at least some knowledge about multiple regression model. Without introducing the multiple regression model, it will be difficult to discuss other estimators. In case of DW test 2, there will be a particular point when, the knowledge of multiple regression is required. However, we will be able to develop, at least give some sense without considering that small part too. Okay, so here it will be better if we stick to one particular measure, that is the Durbin-Watson test. And this is widely used. It's not that it has a number of limitations. However, it has limitation. So let's start with the detection part. Two main ways to detect serial correlation. One is informal, using the graph, etc., analyzing the pattern, as we discussed in context of heteroscedasticity. Now, in case of heteroscedasticity, graphing the matters, etc., theoretically showing these things are easier because, you are plotting the residual with respect to the x variable, one of the x variables at a time. Okay. Now, in case of autocorrelation, again, this kind of plotting is a bit difficult because here you need to plot the two error terms. Okay. So, only with the time series data, if the time period varies, you will get two residuals and then you will be able to plot it. So we will avoid this informal method. we will directly go to the formal method, the testing method. So testing for serial correlation using the Durbin-Watson D-test. Remember, there are number of tests. Even actually in reality we modify the basic DW test as well. However, here I am introducing the idea. So the simple DW test will be enough for this particular course, the general econometrics course. Okay. Now to begin with, we need to understand the context where we will be able to apply the DW test. So first, it is important to note that the Durbin-Watson D-test is only applicable if the following three assumptions are met. Number one, the regression model includes an intercept term. So if I have a model without intercept term, last day some of you raised questions regarding the structure of the model, So many a times we consider a simplified structure because we are interested only about beta, not about the intercept term. However, if you want to detect autocorrelation using the DW test statistic, it is important to have the intercept term in the regression equation. So if the equation is without the intercept term, we will be not able to apply the Durbin-Watson test. Number one. Number two, the serial correlation is first order in nature. Last day, we introduced different series: autoregressive process, moving average process, ARMA process. Okay? And you found that all the series are basically sequence of errors, different orders of errors, or errors with different lags. Now, in case of autoregressive process, we regress UT on UT minus 1, UT minus 2, UT minus 3, and so on, up to UT minus k, say. So, we are moving up to kth order lag. Okay. So, you can think this as the difference equation we considered earlier when we did our math eco courses. Okay, one period lag. In case of cobweb model, in the supply equation, we considered a lag with respect to price of one period. So I can consider a lag of one period. In the Samuelson model, we considered a lag of 2 periods with respect to national income. So it is like that. Autoregressive process is like that. For the same error variable U, we are considering the lags of different orders. So UT is regressed on UT minus 1, UT minus 2 up to UT minus k in general. Now, this DW test will be applicable if and only if our error follows first order autoregressive process, first order AR process, that is AR1 model. So UT should be equal to rho UT minus 1 plus the random error epsilon t. Last day, we explained these first order autoregressive process as the Markov model, and we showed that this first order autoregressive process is equivalent to infinite MA series, infinite moving average process. Now, what is a moving average process? If UT is regressed on different layers of the classical error, epsilon t minus 1, epsilon t minus 2, etc., then the process is called the moving average process. You are considering different lags in terms of error. However, the right-hand side errors are all classical in nature. Okay, left-hand side error is not classic, UT. However, the right-hand side errors, epsilon, are all classical in nature. So this is the moving average process. And ARMA was the combination of the two. So when I am telling that it is applicable to first order autoregressive process, don't think that it is a very, very limited model, because this first order AR is equivalent to MA infinity, moving average of order infinity. Okay. So the DW test has limitation. It always need the first order autoregressive. However, AR1 process itself covers a large number of time period if you convert it in terms of moving average process. Okay. So it is true that the DW test will be not applicable for higher order of AR process. However, it is applicable to AR1 process that indicates it is applicable to MA infinity process. Okay. Rho is the autocorrelation between U and UT and UT minus 1, and epsilon T, as I mentioned, is a classical error. Now, earlier I mentioned, last day I mentioned, autocorrelation is very common in the time series process, and therefore we call it a serial correlation. Okay. And when we are introducing the AR process, MA process, ARMA process, we are bringing the classical error 2 along with the autocorrelated error U. We are bringing the classical error 2. In AR1 process, the error of the model is given by epsilon T, which is a classical error. Okay. In MA process, the entire right hand side is based on classical error. So here I am telling you one term, if anyone takes the advanced course, you will have a small, important, however, very important part of the time series in the advanced course. You will find that this classical error is called the white noise. Okay. Since you are familiar with the term classical error, I am mentioning classical error. However, in the literature of time series, when we introduce this AR1, MA or ARMA, all this classical error is called the white noise. However, there is no difference between the classical error and white noise. We use the term white noise in context of the entire time series analysis. Actually, when we start the autocorrelation, which is the prelude to the time series analysis, we use the term white noise in case of classical error. Classical errors are white noise. Okay. So this is the second assumption. First order serial correlation, first order AR1, first order autoregressive process is required. Number 3, the regression model does not include a lagged dependent variable as an independent variable. Okay. The regression model should not include a lagged dependent variable as an independent variable. So what does it mean? The regression equation is given by yt is equal to beta naught plus beta 1 x1t plus ut. And parallelly, I have another equation here, ut is equal to rho ut minus 1 plus epsilon t. Okay. Now, it is said that the basic regression equation should not be of the form it should not follow this kind of format. That is, here what I have done, I am considering y of different order as the explanatory variable. Okay, so lagged dependent variable as an independent variable. In this equation, I have considered the lagged value of the dependent variable as one of the independent variables, Now, if this is the context, income of this period depends on income of the last period or income of last 5 years. If this is the case, apart from that, it depends on several other things. So if this is the situation, if this is the format of the equation, in that case, you will be not able to apply the Durbin-Watson test to detect whether there is autocorrelation or not. You have to use other technique to understand whether there is autocorrelation or not. Okay, so the regression model should not include a lagged dependent variable as an independent variable. If it includes a lagged dependent variable as an independent variable, in that case, we will be not able to apply Durbin-Watson D test to detect autocorrelation. Okay, so these are the three assumptions without which we will be not able to proceed, or we will be not able to apply Durbin-Watson test. In other words, these are the preconditions of applying Durbin-Watson D test. Any question regarding the assumption? So next, we are setting the test hypothesis or the decision rule. Rho is the correlation between ut and ut minus 1. So if I look at this equation, rho is the correlation between ut and ut minus 1. So naturally, the hypothesis will be rho is equal to 0, no autocorrelation. I mentioned in econometrics, we consider no kind of relation as the null hypothesis. Okay, starting from the very beginning, when we consider the basic model, we consider beta to be equal to 0, which means x cannot explain y. So 0 parameter type hypothesis we consider. In case of heteroscedasticity, the null hypothesis was no heteroscedasticity, that is homoscedasticity. In case of autocorrelation too, the null hypothesis is no autocorrelation, no serial correlation. So rho is equal to 0. And this is tested against the alternative hypothesis rho not equal to 0, which indicates serial correlation. Now, if you look at this equation, ut is equal to rho ut minus 1 plus epsilon t, it is as if a regression equation without the intercept term. Okay, ut is equal to rho ut minus 1 plus epsilon t. Epsilon is a white noise. Okay, so it is as if a regression equation. Okay, and why not then, if epsilon t is a classical error, so why not then the estimated value is summation xi yi, that means ut minus 1 divided by summation ut square. So last day, for the regression model y is equal to x beta plus u, we derived this kind of estimated value for beta hat. Okay, so if the u equation is like that with a classical error epsilon t, why not we will consider an estimator rho hat, which is summation ut minus 1 divided by summation. Sorry. So first you can consider. Okay. This kind of thing you can consider. Now, you may say that if it is a long series, actually in case of time series analysis, we do not consider 5 or 10 observations. We consider at least 50, 60 observations, if not 50,000. Okay. So the minimum size will be too large, so hardly it matters whether you are considering t or t minus 1. So in the denominator, you may suggest instead of considering the lagged error term, you may consider summation ut square. Okay, so all are possible. So an alternative you can suggest rho hat is equal to summation ut minus 1 divided by summation ut square, etc. Okay.
Ma'am,
Whatever be your suggestion, the problem is ut is unobservable. And for that matter, whatever be your suggestion, in the denominator t minus 1, t, it looks like a classical model. So I'll use rho hat is equal to this. All these suggestions will go in vain because ut is not observable. ut is not observable. Okay. So from the very beginning, when we tried to measure the parameters of the model, we could not use u because of the same reason. U is not observable. So we went for some sort of estimator of u, which we call the residual. So whatever be your suggestion, it will not be valid because u is unobservable. So again, you have to consider the natural substitute of u, which is e. Okay, already in the general course, we introduced the notion of residual. Residual is some sort of estimator of u. So instead of using u, the next suggestion will be you use e, the residual term. So you can present an alternative to u or alternative estimator of rho. Acha, excellent, that's. So alternative estimator is given by summation et minus 1 divided by summation et square. Okay, so this can be your suggestion. Okay, however, it can be shown that even if u is not correlated, ui uj is not correlated, then also ei ej will be correlated. Ei and ej are always correlated. Two residuals are always correlated because two residuals are functions of the estimated values of the parameters, which are based on same set of explanatory variables, etc. Now for the formal proof, we need the notion of idempotent matrix. Idempotent matrix, okay? That I'll be able to do if you have some knowledge about the multiple regression model and you have knowledge about how we use the matrix algebra in case of multiple regression model. Without this, in a two variable case, easily I'll be not able to show this. However, using an idempotent matrix in 3 steps, we will be able to prove 2E will be correlated to each other. So please take this line as a note. Okay, so consider this line as a note. Even if U is not correlated, then also E is correlated. Actually, E will be always, 2E will be always correlated. Okay. So for some limitation, I'll be not able to show you the proof at this moment. However, in some later date, I'll be able to show you. Okay, so up to this, you can run the story like this. However, this will also be not the acceptable estimator because it will always show autocorrelation. It will always show autocorrelation. So this is not applicable Because of unobservability, this measure is also not applicable because E is always autocorrelated. Okay, so I have to move for the next suggestion. I have to consider this.
Ma'am,
Summation ET. I'll take question when I'll ask for question. Please ask the question then. In that case, you have to consider. Therefore, as an alternative, we have to consider summation et minus 1 whole square. Okay. So we have to consider this because for summation et minus 1 whole square, we can find that this whole square will be small for positive autocorrelation, large for negative autocorrelation, moderate for no autocorrelation. So these measure responses to the idea of autocorrelation. Now, how when positive autocorrelation, that will be small, for negative autocorrelation that will be large, and for moderate, for no autocorrelation, please think on it. Okay, I'm coming in 1 minute. Could you understand the meaning of the sentence? Anyone?
Yes, ma'am.
How it is happening?
ম্যাম যদি নেগেটিভ অটো কোরিলেশন হয় তাহলে তো মানে একটা পিরিয়ডের সাইন আর নেক্সট পিরিয়ডের সাইনটা চেঞ্জ হতে থাকবে। তো যদি ইটি মানে ইটিটা যদি পজিটিভ হয় তাহলে ইটি মাইনাস ওয়ানটা নেগেটিভ হবে। তো তাহলে ইটি মাইনাস ওয়ানটা একটা বড় ভ্যালু দেবে। আর আহ, আহ, আর যদি ইটিটা নেগেটিভ হয় আর ইটি মাইনাস ওয়ানটা তাহলে পজিটিভ হবে। তো মাইনাস ইটি মাইনাস ওয়ান ওটা আবার বড় ভ্যালু দেবে নেগেটিভে, বাট স্কোয়ার করলে সেটা আবার মানে পজিটিভেই বড় ভ্যালু চলে আসবে। তো তাই জন্য নেগেটিভ অটো কোরিলেশনের জন্য সামেশন হবে, তো লার্জ হবে ভ্যালুটা।
একটু সোজা করে বলি, তুমি যেটা বললে সেটা একটু হোল স্কয়ারটা এক্সপ্যান্ড করলে করে তুমি ঠিকই বলছো, এটা একটু সোজা করে বললে বুঝতে সুবিধা হয়।
হোল স্কোয়ারটা এক্সপ্যান্ড করলে
ধরো এরকম লিখলাম, ঠিক আছে?
হ্যাঁ ম্যাম।
এই দুটো তো পজিটিভই হবে সবসময়, স্কোয়ার আছে বলে।
হ্যাঁ
ইটি ইটি মাইনাস ওয়ান পজিটিভ অটো কোরিলেশন যখন,
আর আর ম্যাম ওই -2 ইটি মাইনাস ইটি মাইনাস ওয়ান এটা সবসময় পজিটিভ হবে, মানে এই পুরো জিনিসটা মাইনাসটাকে নিয়ে।
when কেন পজিটিভ হবে কেন যখন ইটি
ম্যাম পুরো জিনিসটা মাইনাসটাকে নিয়ে বলছি।
when there is positive autocorrelation between et and et minus 1, তখন এই পার্টটা পজিটিভ,
হ্যাঁ হ্যাঁ
part is positive,
হ্যাঁ
okay? So it will be minus, ঠিক আছে? যখন this is negative, this entire thing is positive, okay? So when there is positive autocorrelation, this value is smaller because I'm subtracting something. When there is negative autocorrelation, then I am adding something, so the value will be large. And when there is no correlation between these two, this part will vanish, so it will be moderate. So when no presence of this part, it will be some et square plus et minus 1 whole square. So it is moderate. When the correlation is positive, something will be subtracted, so it will be small. When the correlation is negative, something will be added, so the value of this whole square will be large. This is the idea. Is it okay to everyone? How this summation et minus 1 whole square can respond to small positive, can respond to positive autocorrelation, negative autocorrelation, and no autocorrelation. In case of positive autocorrelation, it will be small. In case of negative autocorrelation, it will be large. And in case of no autocorrelation, it will be moderate. Now, please check and tell me if anyone have any question up to this. This slide and this slide. Up to this. Yes. One by one, yes.
হ্যাঁ ম্যাম, বলছিলাম যে আপনি ওই আগের যে ডিডব্লিউ টেস্টের আগের স্লাইডটাতে একবার যান।
Yes.
হ্যাঁ, ওইখানে যে আপনি ওই স্ট্যাটিস্টিকে ইউটি মাইনাস ওয়ান স্কোয়ারটাকে ইউটি স্কোয়ার কি করে মানে কেন ইয়ে করলেন, মানে ইন্টারচেঞ্জেবলি ইউজ করলেন?
Time series, for time series data, we will consider generally a long period data. We will not do 5 period, 10 periods. Generally we consider a long period. Otherwise, time series we use for the macro analysis. It is the macro part of the econometrics. So in case of macroeconometrics, generally we use a long database. Otherwise, there will be no meaningful analysis actually. So it doesn't matter whether you are considering last 50 years or 49 years, okay? Or last 500 years, 500 time points, or 499 time points. Okay, it is just like the concept of infinity. It doesn't matter much if it is a long observation series, long observation. In case of MLE2, you found when you are considering a large sample, it doesn't matter whether you are considering n or n minus k. So following that similar logic, if the number of observation is large, generally in case of any time series analysis, number of observation will be large. Otherwise, we will be not able to go for the meaningful analysis. So if the number of observation is large, I hope you are understanding, it doesn't matter if you consider -1. Okay.
Yes.
So that
Ma'am,
later also I'll explain all these things, when we will present the right D statistic, in that case too, I'll again repeat the things, every point I'll repeat. Yes, next question, yes.
ম্যাম ওই এপসিলন টি এর নিচে কি লিখেছেন ওটা বুঝতে পারছি না।
হ্যাঁ,
ওই যে এপসিলন টি এর নিচে ওই তীর দিয়ে একটা জিনিস লিখেছেন না।
হোয়াইট নয়েজ, এই আগের স্লাইডে বললাম যে হোয়াইট নয়েজ।
আচ্ছা আচ্ছা আচ্ছা।
Okay, you are familiar with the classical error term, therefore I'm using that. However, as I mentioned, in a time series analysis, we replace the term classical error by the term white noise. Any other question regarding the first sentence in this slide? Is it clear to everyone? Here, we generally use Durbin-Watson statistic, which is denoted by D. Durbin-Watson, there is some a problem of unobservability with U. There is problem if I use E, if I use Wallace kind of estimator using E will be always correlated. Okay, the third thing is summation ET minus 1 whole square can work here. So joining all these things, Durbin established or derived a statistic denoted by D. Now, what is D? D is equal to summation ET minus 1 whole square, this thing, divided by summation ET square. Okay. So Durbin used this statistic, developed this statistic to detect autocorrelation. Okay. ET, he is using as the reference period. Okay. So, and as I mentioned, if it is a long series, it doesn't matter whether you are considering T or T minus 2 or T minus 1, etc. So following this logic, Durbin considered T as the reference, Tth period as the reference, current period as the reference, So in the denominator, he used ET. And in the numerator, he used this idea, which has been written first as the first point in this slide. Summation ET minus 1 whole square will be able to capture the essence of positive, negative, no autocorrelation. So why not we will use this thing. Now, while taking the sum, in the numerator, the range is from 2 to n. Why? Because if t is 2, then t minus 1 will be 1th period. Now if I consider t to be 0, in that case t minus 1 will be minus 1th period. If I consider t to be equal to 1, then it will be E1 minus E0. So all these things are coming. So to avoid the 0 and negative values, without losing any generality, in the numerator, we are considering the time from 2 to n. And since n is too large, it will not be at all a problem. In the denominator, there is simply et square instead of et minus 1 square. So since it is et, we can start with 1. So it is a specific statistic, In the numerator, the range is from 2 to n. In the denominator, the range is from 1 to n. The logic is always we will be able to have a positive number, The basic will start from 1. In the numerator, there will be 2 minus 1, this kind of thing, E2 minus E1, and in the numerator, and in the denominator, there will be E1 square, the first observation, Then there will be E2 square, E3 square, and it will move, up to the last time period you are considering. Next, we are spreading the whole square. So, a square plus b square minus 2ab, a square plus b square minus 2ab, that we are considering. Range is from 2 to n in the numerator. Denominator, you can replace these by 2 to n, because in the next step, we will go for some cancellation. So instead of 1 to n, you can replace it by 2 to n. For everything, the logic is same. Since the sample is large, we are doing all these things. Since the sample is large, we will be able to make this kind of adjustments without losing any generality. Okay. Now, in the numerator, we have summation t is equal to 2 to n et square, and summation t is equal to 2 to n et minus 1 square. These two things, according to Durbin, or running several experiments, they found that these are approximately equal to each other. If you consider one period less and find out the residual value, in 7th or 8th decimal place, there will be some small change. So these are equivalent. These are equivalent. So these are approximately equal if the sample is large. So in the numerator, I am writing 2 summation et square. Let me write. Minus 2 okay. So if I write this thing, so 2 summation et square divided by summation et square will give me 2. And this will give me 2 rho hat. where rho hat is summation et minus 1 divided by summation et square. So this is equivalent to this is called the D statistic or Dobbin-Watson statistic, D. D is approximately equal to 2 into 1 minus rho hat. D is approximately equal to 2 into 1 minus rho hat. So this 2 into 1 minus rho hat is the Dobbin-Watson's D statistic. Using D statistic, Dobbin and Watson showed how we can detect autocorrelation, how we can detect the presence of autocorrelation. Any question? If rho hat is plus 1, so finally what is the value? D is equal to, this is the thing. So if rho hat is equal to 1, you are finding D to be equal to 0. If rho hat is equal to minus 1, so 2 into 2, D will be 4. And if rho hat is equal to 0, in that case, D is equal to 2. Now the extreme value of the correlation or the maximum value of the correlation between two variables is 1. If the, if the points lie on the fit, perfect correlation. The measure of perfect correlation is given by the value plus minus 1, whereas no correlation, that is captured by the value 0. So what we are finding that D is equal to 0, that indicates perfect positive correlation between the two error terms. D is equal to 4, that indicates perfect negative correlation between the two error terms. D is equal to 2 indicates there is no correlation between the error terms. So in other words, if D is close to 0 or 4, the residuals are highly correlated. If D is close to 0 or 4, in that case, the residuals are highly correlated. Alternatively, if D is close to 2, if D is close to 2, in that case, the residuals are not correlated. Okay, so if residuals are close to the value 2, in that case, no correlation. If they are close to either 0 or 4, in that case, high correlation. Okay. So we can think about this kind of number line moving from 0 to 4. So if the value is close to, this point or this point, in that case, that will be the indication of what? If the value is close to the last 2 points, that will be indication of
autocorrelation.
Autocorrelation, yes. High autocorrelation. And if the value is around 2, the middlemost point, in that case, that will give indication about no autocorrelation. Now there is some problem, when you are calculating the D statistic on the basis of observation, it, never actually you will get the value 0, 2, 4, this kind of values. These are accidental values. That is, you are calculating the things and you are getting the value 0 exactly, 2 exactly, 4 exactly. These are only the accidental things. So Dobbin and Watson prepared a table where they marked two other values, dl and du. dl is the lower limit, du is the upper limit. If the value lies below dl, in that case, high correlation. If the value lies above du, high correlation. And since 2 is the middlemost point, what they did, they folded the line. They folded this line. Okay, so this part will come in this part as 4 minus d. Okay, they will not consider this part in the table. Rather, they will consider 4 minus d to include this part in the first zone. Okay, so they will talk about this dl, they will talk about this du, and they will also talk about 4 minus d to come to your conclusion. Okay, now I'll come to the point that between the zone dl and du, the test remains inconclusive. I'll come to the point. Before that, I like to add certain things about having dl and du. Okay, dl and du. So this,
ম্যাম বলছিলাম যে এই আগের স্লাইডটা দেখান, আগের স্লাইডটা।
Nartok, I told you when I'll ask for question, please ask the question in that case. Okay.
ও
Statistic D depends on X size, explanatory variables, and hence no general cutoff points can be obtained. So what I am telling that the statistic D, the Darwin-Watson statistic, is a function of explanatory variables. How these are function of explanatory variables? These are based on EIs, and EIs are functions of explanatory variables. EI is yi minus yi hat. Okay, so when we are writing yi and yi hat, these are the function of X size. Actually, if I use the multiple regression model, as I mentioned, I can show you EI is equal to M into U, where M is an idempotent matrix prepared by X variables. Okay, so I could not show you that part because I could not introduce the multiple regression so far. Therefore, I avoided that part. However, remember that E is a function of X. And for that matter, D, which is based on E, is function of X. So statistic D depends on X size, and hence no general cutoff points can be obtained. It is a function of X size, so you know it will vary. So no general cutoff points can be obtained. However, two other statistics, DL star and DU star, have been developed such that D is stochastically larger than DL star and smaller than DU star. So Darwin and Watson tried to find out two specific values, DL star and DU star, or two specific statistics, DL star and DU star, which are independent of X size. Which are independent of X size. So these will prepare the table. You know, DL star and DU star are marked values. After several research, they got these 2 points or identified these 2 points which are independent of X size. These are externally given, DL star and DU star. So from these distribution, the critical points DL, DU, independent of X size, can be obtained. If D is less than DL, there will be positive autocorrelation. If D is greater than DU, no autocorrelation. So if D is less than DL, that is in between 0 and DL, you know, infinite number of values in between 0 and DL, in that case, positive autocorrelation. If D is greater than DU less than 2, anywhere between DU and 2, in that case, there will be no autocorrelation. There will be no autocorrelation. For measuring the negative autocorrelation, you have to consider 4 minus D. For measuring the negative autocorrelation, we have to consider the value 4 minus D. We have to consider the value 4 minus D. If 4 minus D is less than DL, if 4 minus D is less than DL, in that case, okay, so this is the idea. Using statistical tables, we may test the hypothesis of zero autocorrelation against the hypothesis of first order positive autocorrelation. First order positive autocorrelation, it itself captures the idea of negative autocorrelation too. Negative autocorrelation too. Okay, because as if we folded the line. In case of normal distribution, many a times we do this. We do not consider the left part, as if we are folding the left part on the right part. The same kind of thing. Here I am folding the right part on the left part. So, we can summarize the steps as follows. Null hypothesis is rho is equal to 0. It is tested against the alternative hypothesis rho not equal to 0. If D is less than DL, reject H naught. Reject the null hypothesis of no autocorrelation. That is, it indicates positive autocorrelation. If D is, your calculated D is greater than 4 minus tabular value DL, reject H naught. Because this indicates negative autocorrelation. If 4 minus DU greater than D greater than DU, do not reject H naught. Do not reject H naught. If D greater than DU or 4 minus DU greater than D, for the other part, when you are coming back from the the right hand side. If 4 minus DU is greater than D, or if you find D is greater than DU, D is greater than DU, okay, D value is greater than DU, okay, in that case, do not reject H naught. However, the limitation of DW test is, if your value lies between DL and DU, the test remains inconclusive. That is, the test remains inconclusive in this zone. The test remains inconclusive in this zone. You will be not able to come to any conclusion if your calculated D value lies in between the tabular values DL and DU. If your calculated D value is, lesser than DL, you will be able to come to some conclusion. If it is greater than DU, however, within 2, you will be able to come to some conclusion. However, your calculated value, if it lies between the two limit DL and DU, in that case, the test remains inconclusive. When we will go for some numerical exercises, I think the things will be more clear to all of you. Now the question you have. Please check this. I'm coming. বলো কোয়েশ্চেন্স গুলো এবার, দর্পক বলো এবার কি বলছিলে।
হ্যাঁ ম্যাম, বলছিলাম যে আগের স্লাইডটায় যাবে যেখানেতে,
এর আগে,
হ্যাঁ 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 এখানেতে যাবে।
হ্যাঁ বলো।
আমি লেখা হয়নি, একটুখানি ওই লিখে নিচ্ছি।
লেখার তো কিছু নেই এখানে।
না ম্যাম, আপনি যেটা লিখেছেন হয়ে গেছে ম্যাম, ওই বাস।
এবার কার কি কোয়েশ্চেন আছে বলো একটু।
Ma'am,
হ্যাঁ বলো।
ma'am, D greater than DU implies no autocorrelation. That is because we have folded the negative autocorrelation part onto that side, right? T এর
হ্যাঁ মানে 4 - d করে করে নিতে হবে। তোমার
Yeah.
নেগেটিভ অটো কোরিলেশনের জন্য দেখো 4 - dl 4 - du, এইভাবে তোমায় চেক করতে হবে। 4 - d কনসেপ্টে চলতে হবে। মানে তুমি টেবিলটাতে ডি টা পেয়ে গেলে ডি আর 4 - d এর ভ্যালু গুলো তোমায় চেক করতে হবে।
Okay, ma'am.
Okay, so again from Madala, you will get workout exercise there. There is one workout exercise there. Okay, they are using table 3.11 from the book. You will get that table 3.11, that was a production function, estimation of a Cobb-Douglas production function. So look at the structure of the equation. It is the logarithmic transformation because originally the function was in the Cobb-Douglas term and then it was estimated using the the logarithmic transformation of the model. So log x is equal to this value. So this estimation part is already over and you know how to estimate the parameters, etc. Though it is a model where there is more than one explanatory variables, So maybe in the next week I'll introduce the multiple regression model, more than one explanatory variables, okay? So it looks like, or all the logic will be similar to that of the two variable model. So, this is the estimated model. So you will learn how to estimate the parameters when there are more than one explanatory variables. And there is R square, the typical thing is there is the calculated DW statistic, 0.88. The DW statistic has been calculated. Actually, when the model is there, you will be able to calculate the residual, and on the basis of the residual, if it is a time series data, you will be able to calculate the DW statistic. So this is the DW statistic. And also there is a value of rho hat, 0.559. Referring to the DW tables with K prime is equal to 2 and N is equal to 39. K is the number of parameters, So here the number of parameters, it is considering the number of parameters without the intercept term, K prime minus the number of intercept. N is equal to 39. For the 5% significance level, then they are checking DL value is 1.38. And since the observed D is less than DL, therefore reject the null hypothesis of zero autocorrelation at 5% level. Okay, so there is a workout. So please check that. Okay, next day again I'll talk about this, but before that, please check the Darwin-Watson table that is at the end of Madala's book. Darwin-Watson table you will not get from the statistics books. In the econometrics book, you will get the table. So it is a standard table like, T, chi-square, F, tau, So So it is a standard table. So have some idea about this table and check the workout example. I'll discuss, several examples or how to do these things in the next class. Okay, so numerical exercises, I'll start from the next class. First, let me complete the theory part, and from the next class, I'll discuss some numerical exercises on heteroscedasticity and autocorrelation and cover all these aspects. So any question in the theoretical part? Otherwise, I'll go for the remedy. Any question on the detection part? Remedial measure. Already we proved that beta hat OLS is no more the best linear unbiased estimator. Unbiasedness property is retained, however, the estimator is not at all a best estimator. Okay? So, we have to do something so that we can find out the best linear unbiased estimator. Once the autocorrelation is detected from the database, how we can proceed to have a best linear unbiased estimator, this is the last part of the autocorrelation analysis. Okay, now there are several things. If it is a pure autocorrelation, we have to proceed in some way. If it is impure autocorrelation, we have to proceed in other way. In Madala's book, you will find that if, there is the autocorrelation developed from omitted variable, if there is autocorrelation developed from misspecification, so there are tests to detect autocorrelation in, using several techniques so that we will understand whether the autocorrelation is coming from the omitted variable, whether the autocorrelation is coming from the misspecification. So if these are the case, the remedial method will be something. However, as I mentioned, to reduce the size of the codes, still I didn't introduce the multiple regression. So we cannot discuss a number of things which are based on omitted variables, misspecification, etc. So at least in the simplest framework, to introduce the concept and to understand the detection and the remedial technique, we are keeping the model, the two variable model, okay, and discussing the matters. So at this moment, I'll not discuss anything if the autocorrelation is detected from the omitted variable context or autocorrelation is detected from the misspecification context, what will be the remedial measure? Rather, if it is a pure autocorrelation, that is, it has been developed because of the fact that the error in the original regression model is not a white noise, it is not a classical error, then what will be the remedial technique? If the error in the original model is not the classical error, if the error in the original model is not a white noise, in that case, what will be the remedial technique? What will be the remedial technique? So remember, the remedial technique you are learning, that is not applicable for all the cases. The remedial technique you are learning, that will be applicable if the source of autocorrelation is because of the fact that in the original model, your error is not a white noise. Okay. The technique is in general called the generalized least square technique. So let's see what is meant by generalized least square technique. Okay. In context of a simple model, or in context of the case where the original the error in the original model is not a white noise. So start with an equation. that has the first order serial correlation. First, start with an equation that has serial autocorrelation. So here there is a change in the notation. I marked this change before the class. However, I didn't change it. So if for your convenience, you feel that the error in the original model, you will keep UT, and here you will consider, the term epsilon t, which we did in the first few equations. Please do that. I didn't get time to change all these things, so এটা একটা নোটেশনাল ম্যাটার্স হয়ে গেছে। বুঝতে পারছো তো আমি কি বলছি? আমি হেন্স মানে এর আগে পর্যন্ত অরিজিনাল মডেলের এই এররটাকে ইউটি ধরেছিলাম, আর ফার্স্ট অর্ডারের ক্লাসিক্যাল আর হোয়াইট নয়েজ কম্পোনেন্টটাকে ইপসিলন ধরেছিলাম। এগুলো সব ইউটি ছিল, ইউটি -1 ছিল, আর এটা ইপসিলন ছিল। তো এটা একটা আমার চেঞ্জ হয়ে গিয়েছে। However, you can consider these as a fresh model, so I hope nobody will face any problem. So start with the equation, with an equation that has first order serial correlation. Okay, so the equation is given by yt is equal to beta naught plus beta 1 x1 t plus epsilon t. So for epsilon t, these are the assumptions. If I write the assumptions, I hope nobody will have any confusion. Okay, so it is autocorrelated. Epsilon t is autocorrelated. Covariance between epsilon t and epsilon s is not equal to 0. And the second equation we are considering, that is epsilon t is equal to rho epsilon t minus 1 plus ut. Okay, now this ut is a white noise. Okay, so ut is a white noise. For this, expectation is 0, variance are constant, covariance between two errors, that is also equal to 0. So it is a white noise. Okay, so yt is equal to beta naught plus beta 1 x1 t plus, in place of this epsilon t, I'm bringing rho epsilon t minus 1 plus ut. Okay, so I'm replacing epsilon t by the second equation, rho epsilon t minus 1 plus ut. Okay, then I'm multiplying the original equation by rho, and then lag the new equation by 1 period. So first I'm multiplying this by rho, so rho yt plus, equal to rho beta naught plus rho beta 1 x1 t plus rho epsilon t. And then I'm lagging the time by 1 period. So ultimately the equation will look like this: rho yt minus 1 plus rho beta naught plus rho beta 1 x1 t minus 1 plus rho epsilon t minus 1. So this is the form. So equation 5 was the origin, 5 was originally there. I'm multiplying this entire equation by rho, and lagging the time by 1 period. Lagging the time by 1 period. Okay. So this is equation number 5, this is equation number 6, and this is equation number 7. Then I'll subtract equation 7 from equation 6. So yt minus rho yt minus 1 will be the left hand side. Beta naught into 1 minus rho will be the first term. Then beta 1 common, x1t minus rho x1t minus 1. Okay. This rho epsilon t minus 1 and rho epsilon t minus 1 will be cancelled, and you will left with only ut. So I'll request everybody, please subtract equation number 7 from equation number 6. Please subtract equation number 7 from equation number 6. Left hand side will be yt minus rho yt minus 1 equal to beta naught common into 1 minus rho plus beta 1 common x1t minus rho x1t minus 1 plus ut. Understood the equation?
Yes, ma'am.
Please tell me, what is the speciality of this error? What will be the speciality of the error in the new equation? What about the error? What is the nature of ut? When you are subtracting and getting only ut, is ut autocorrelated or ut not autocorrelated?
Non-autocorrelated.
Not autocorrelated, okay? Because ut in our model is not autocorrelated, it is a white noise. So when we are converting the equation and getting the error term in the equation, that is not autocorrelated. So if I estimate the parameters using this equation, if I calculate beta 1 hat using this equation, will it be best linear unbiased estimator or not? Yes or no?
Ma'am, could you repeat that? I didn't understand that last part. Could you repeat that?
This is the final equation, equation number 8, where error is a white noise. Now, if I apply the ordinary least square technique to estimate beta 1 using equation number 8, will beta 1 hat be a blue best linear unbiased estimator or not?
Ma'am, it should be blue
It should.
Yeah.
Very
because
good.
UT is a white noise.
Yes, UT is a white noise. If UT is a white noise, if I apply OLS, we will get blue, because Gauss-Markov theorem will be satisfied in that case. Okay, so beta 1 hat, as Olipriya is telling, should be a blue, best linear unbiased estimator. Okay, so this is the mechanism, this is the remedial technique. This technique is called the row differencing technique. It's a new equation. Here I am regressing yt minus rho yt minus 1 on x1t minus rho x1t minus 1. Or in general, I can say I am regressing yt minus rho yt minus 1 on xt minus rho xt minus 1. So I am not regressing y on x, rather I am regressing yt minus rho yt minus 1 on xt minus rho xt minus 1. So if I convert the model in this way, if I transform the equation in this way, I am getting back the white noise and I am getting back the best linear unbiased estimator if I apply OLS on this. Okay, so finally equation 8 can be presented as yt star is equal to beta naught star plus, remember, rho is a constant. The correlation between error terms, that is a constant. So I can rewrite beta naught into 1 minus rho as another value beta naught star. So yt star is equal to beta naught star plus beta 1 x1 t star plus ut. This is called the rho differencing method. This is called the rho differencing method. This rho differencing method will give us the best linear unbiased estimators of the parameters of the model. Okay. The meaning of yt star, as I mentioned, yt minus rho yt minus 1 x1 t star is x1 t minus rho x1 t minus 1 beta naught star is equal to beta naught minus rho beta naught. Okay. So this is the rho differencing method. Many a times we consider the value of rho to be equal to 1. Value of rho to be equal to 1. If the value of rho is equal to 1, the regression equation can be written as it can be written in this format. If rho is equal to 1, equation can be written in this way. This is called the if you consider rho to be equal to 1, we call the equation the first difference equation or first differencing method. Okay. General is this version. If rho is equal to 1, we can write the equation in this format. Okay. So this is the rho differencing or the first differencing is giving us the remedial technique in presence of autocorrelation to get back the best linear unbiased estimators of the parameters of the regression model. Equation 9 is called the generalized least squares or quasi-differenced version of equation 5. Note that the error term is not serially correlated. As a result, OLS estimation of equation 9 will be the minimum variance. B, this is true if we know rho or if we accurately estimate rho. Okay, so this we will be able to do if we know the value of rho or we can accurately estimate the value of rho. Okay, so the slope coefficient beta 1 is the same as the slope coefficient of the original serially correlated equation 5. Thus, coefficients estimated with GLS, the gradient coefficient estimated with GLS have the same interpretation, same meaning as those estimated with OLS. When we are considering this kind of transformation, I hope already you marked, though the structure of the intersect term is changing, the structure of gradient term is not changing. The structure of the regression coefficient, if you go for the rho differencing method or if you go for the first differencing method, that is not changing at all. So interpretation of all gradient coefficients will remain unchanged over the OLS and the GLS model. Okay, So interpretation of all beta 1 hat, beta 2 hat, if there are more than one explanatory variables, that will remain unchanged for the original model and the transformed model. For the original model and the transformed model. Any question? Any question on the method, on the conclusion, etc.? Okay, so if you understand all these things, the last point, please take note of the last point, I think. Yeah, the last point. The dependent variable has changed compared to equation number 5, you know. In equation number 5, we are considering a regression of y on x, whereas when we are deriving the best linear unbiased estimator, we are considering a regression of yt minus 1 on xt minus xt minus 1, or yt minus rho yt minus 1 on xt minus rho xt minus 1. So though the interpretation of beta hat remains unchanged across the OLS and the GLS model, don't think that the two models are comparable. Actually, you are considering two separate regression. Your variable space has been changed. Initially, you were at xy plane, and now you are at y minus rho y, or yt minus rho yt minus 1 and xt minus rho xt minus 1 plane. So the space, you know, at which you are deriving the results, that is changing. So the two regression equations are no way comparable. So if you find that R square of the previous model is good compared to this one, you will stick to the original model. Or if R square of this equations are better than the previous one, you will come to this structure. Okay, all these conclusions are wrong conclusions. Okay, we cannot compare the R square of these two models. Okay, so the original model is called the level equation, and the transformed model is the row difference or first difference these two equations are not comparable, you know. So level equation is not comparable with the difference equation. Okay, so up to this is more than sufficient. We are not talking about the forecasting or prediction in context of autocorrelation, heteroscedasticity. We are not doing these things in this course. Okay, so you can avoid the fourth point or the last point. Okay, you can remember that for the further analysis, that is for the hypothesis testing, etc., you will consider the new model, because the new model is giving you the best linear unbiased estimator. So for the future things, you know, once you get the parameter of the model, for rest of the applications, that is for the hypothesis testing, prediction, forecasting, whatever, you have to use the result of the final model, result of the transformed model, because the transformed model is the right model. Transformed model is giving us the best linear unbiased estimator. So this is all for autocorrelation. This is all for autocorrelation. So next we have to discuss the true false type question, numerical exercises. First you check the exercises of heteroscedasticity and autocorrelation. So next few days I'll spend on solving the problems on prediction, problems from heteroscedasticity, autocorrelation. Next day or next 2 days I'll spend on this. So please go through all these things, otherwise when we will go for the numerical exercises, etc., those classes should be interactive classes. Otherwise I have to move for the theory. Any question? Any question?